So somehow compact formulation takes some practice. So let me give you one more example. This is for our product mix problem. So our product mix problem, let's generalize it instead of just looking at the desk and the tables. Let's say we have n products to be produced and they need to consume m number of resources. Okay, m different types of resources. So n and m can be any number. If you are running a semiconductor fab, then n may be thousands, and m may be also thousands. Okay, so we are going to use j and I to be the indexes for products and resources respectively. So it's a very good habit to maintain the use of indexes throughout your whole program. We're going to require ourselves in the case that when we say j, everybody knows it's product. When we say I, everybody knows it's resources throughout the whole formulation. Okay? From time to time, this may not be so easy, but if you try to enforce yourself to do that, in many cases, you will get satisfied formulation. So we need some parameters. Unit sales price of product J is going to be PJ. The resource supply limit is Ri. And the unit of resources are unit of resource I required for producing 1 unit of product J, that's denoted as Aij, and so on. So you may see that whenever we are talking about resources, that's I. Whenever we are talking about products, that's J. And once we have that, we're going to define Xi as the production quantity for product I is from 1 to n. And then we are able to write down our compact formulation. So because here there is a parameter that takes 2 indexes, well, you may need to spend a few minutes to work on it to really understand what do we mean. And maybe you need to take a look at the simple formulation with desks and the tables. But anyway, let's understand this. I want to maximize the total revenue I have. So depending on my production quantity and the sales quantity, depending on the price, I may collect the sales revenue for all the n products. That's my objective function. For each constraint, the limit is there. The limit is there. So I only have Ri unit as my resource I, and this particular thing is the amount of resource I need. Okay. So for resource I, according to the product I want to produce for product 1, xj, xi, x1, I'm going to consume ai1 times x1. For x2, as my production quantity for product 2, the total consumption is ai2 times x2, and so on and so on. So the collection here, the summation here, is the total amount of resource I use. Of course, cannot be greater than the total amount I need. Finally, everything should be non-negative. Okay? So interestingly, sometimes we may use an even more compact formulation. So we may define set for the set of products, set of resources, or in general, index sets. Okay, index sets. So why do we call them index sets? Because the set contains indexes. Here, this is the indexes for products. That is the indexes for resources. Once we do that, here you don't need to write down j from 1 to n. You only need to write down for all j that's in the set, capital J, that's collect pjxj. For each resource I in the set I need to do this calculation again by considering all possible products, something like that. So the two formulations in this page and in the previous page, they are obviously identical or equivalent, all right? But you may choose the one that you feel more comfortable with. For me, I almost always write in this way because it saves me some spaces, saves me some time. The last page is some concept that we will use throughout whatever you call it, a course, a semester, whatever. It's the difference between problems and instances. So this is something to know in general, not just for linear programming. But now this is the right time to introduce this. A problem is a collection of instances. It's an abstract description of a task or a question. Whenever we are expressing things with symbols, we are defining a problem or a class of instances. An instance, on the other hand, is a realization, is a concrete realization or a concrete specification of a problem. When we plug in concrete values into those symbols, we are obtaining an instance. Okay, so we obtain an instance. So these examples are here. A compact formulation look in this way. Okay, everything are in symbols. And once we plug in values, that becomes an instance. So if you are running a factory, today you solve a problem. After you have some new products, you solve a new instance. Okay, because in the abstract setting, you are still talking about the same problem. It's just that the numbers, the values, the parameters changes. You have more product, it's just n becomes larger. If the cost becomes different, you are still solving the same problem. It's just that the instance becomes another one. Okay? If you have two factories doing pretty much the same thing, you are solving the same problem. It's just that you are dealing with different instances. So one reason to write formulations is because once you have a formulation for one problem, it helps you to deal with all different kinds of instances. Instances may change from day to day, from time to time, from location to location, but it's quite possible that their problem is actually the same one. And eventually you will learn it that whenever some people are trying to invent algorithms to solve, for example, linear programs, to solve problems, pretty much they are dealing with problems. Okay, so once we have a model, that's a problem, and once we are able to solve a problem, we are able to solve all those instances. So this is the first time I talk about this idea, but from time to time in later lectures we will see this from time to time. So this is actually very important. Once you know it, you really get deeper understanding about the whole thing about operations research.